Hi, I'm Dave Robinson, and welcome to a screencast where I'm going to be solving a puzzle from the Riddler. So the Riddler is a great column by 538, and this week's puzzle, the Riddler Classic, looks like a question about rolling a die. So I think it's going to be a great example of doing a simulation in R to solve a puzzle. So let's take a look. You start with a fair six-sided die and roll it 6 times. Recording the result of each roll, you write these numbers in the 6 faces of another unlabeled fair die. If yours were 3, 5, 3, 6, 1, your second die wouldn't have a 4 in it, would have 2 3s. Okay, you roll this again and again and again. Eventually you'll roll a die with the same number in all 6 faces. What's the average number of rolls we'll take to reach this state? So this is a great problem for simulation because it's going to show what we call a recursive relationship between each step. That is, each step has to depend on the previous step. And for that, we're going to be doing a, we're going to be using a function from per called accumulate. So let's save this. It'll be Riddler, what is it called? Die reroll. All right, and I'm going to do a simulation here. For starters, what we'll say is we start with a fair six-sided die. So I'm going to say start with 1 to 6. Now, I'm going to do one simulation before I put this into a function. The way that I would do one simulation would be sample, start, 6, replace equals true because you're rolling it fairly with replacement. This one I have 3, 3, 5, 5, 2, 6. So it's as if we would do, I can't call it next. Next rolls will be this, and then we keep repeating that every single time. So we could just keep copying this. We could do blah-de-blah-de-blah. But the way we're instead going to do it is with the per package. In fact, I'm going to load up the tidyverse just for kicks, and we're going to do this with per's accumulate function. Accumulate is really handy. What it does is say, from the 1 to 10, let's accumulate, let's run again and again, sample dot, tilde for function, dot 6, replace equals true. Actually, yes, I can just do sample 6, replace equals true, and do dot init equals 1 to 6. That's what we're doing. Oh, notice that. In this case, 5s became, they showed up here. So what happened is, this actually accumulated. It started with 1, 2, 3, 4, 5, 6, then 6, 1, 2, 5, 1, 5. I'm actually curious, if I didn't give it 6, that's great. If I don't give it 6, what it does is it just does the sample. So I can actually make it even a little easier. Look at that. I could just sample like this. Now notice the first one is always going to be 1, 2, 3, 4, 5, 6, but initialize. Then we say this is the next one, next one, next one, next one, and so on. And eventually it all goes, not in this case. We do 20 steps. Eventually it ends up all with one die, and that's what we're looking for. So how can but I want to know, when does it become all one die? So notice first, what I've done here is I've done accumulate that returns a list of iterative steps. Here's what I'm going to do. I'm going to change this to function. So accumulate, notice then, is very good for these recursive relationships. But I'm going to change this to function. Why am I doing this? Because I'm going to say result. Now, I need to actually, so far it's just the same thing. I need to say if they're all the same. So actually, if length unique of result equals 1, then I'm returning done of result. And done is a function from per that's like a signal. It's a box that is early termination of the accumulate step. So then what I'll do is I'll say if that, then done, otherwise result. Else, let's see. Length this. Done. I'm missing a step. I'm missing something here. Function out. Oh, it can't just be a dot. It actually needs, I'm going to call it x. Problem is that the function actually gets a couple steps, including whatever it's doing. So here it happened on this was the 0th roll, first roll, and so on. and then it happened on the 12th roll. I'm just curious, how do I have to say, yeah, I'm going to keep this. Okay, yes. So what happened then is it kept the 0th roll, 1, 2, 3, 4, 5, 6. That's not actually a roll. There were 11 rolls. And on the 11th roll, I'm just checking how this is defined. What is the average number of rolls it'll take to reach this state? Yeah, this was the one that got all 5 5s. Okay, so that's the simulation. Can I compress this at all? Not like, not really. This like if else is a little bit, it's a little bit more complicated than the rest of it. And to say if length unique result is this, yeah, it's really pretty good. So the last thing I'm going to do on this is say, so this is simulate roll function num sides, I'm actually going to say. And now this 1 to 20 isn't actually meaningful. It just sets a max. It's like, what is the maximum number of steps you're going to try? So I'm going to accumulate across this 1 to 100 every time applying this function. I didn't really talk about what accumulate does here, but check it out. It's great for these recursive relationships. And what I want to do is say, I can do simulate roll of, I'm going to make num sides equal to 6 by default. Simulate roll, here we go, here we go, here we go, here we go. Notice each time it takes a different number of steps. I'm going to say here rolls, and then I'm going to return length rolls minus 1. So because y minus 1, because we did the first result is just 1, 2, 3, 4, 5, 6, as if it never happened. So there we have simulate roll 1. All right. So then I'll say simulations is we're going to repeat this many times. There's many ways to do this. I kind of like this built-in R function called replicate that just runs that function a whole bunch of times. And if I did a histogram of simulations bin width 1, I actually get this, I get a distribution out. It looks like I can do 1,000 pretty well. I can do 10,000. It's not, so what is the distribution? So I note a couple things I would note about it. It's not monotonically decreasing, which means it's not an exponential distribution where the probability of something happening in each step is equal. There's a clear mode here. Could it be a log? Could it be a gamma distribution? Yes, absolutely. A gamma distribution looks like distribution. Could it be a gamma distribution? Yeah, it looks kind of like this. I'm not so sure it's a gamma distribution. But it could be a log normal distribution. No, it can't because it's 1, 2, 3, and so on. And also gamma's numeric, so well, I'm not really sure how to model it yet. That's not really the question. The question is what's the average number of rolls it would take. First, I'm going to add a one extra order of magnitude in here and say let's do 100,000, and we're going to see how long does it take. That takes a minute. But notice, yeah, that was the steps that I did. I wrote a little function. This is the only step that actually resampled based on whatever the previous result was. But the yeah, it's taking a little longer than I wanted it to. Next time I run it, I'm going to do 10,000. But yeah, and then it'll say, because it never really takes more than 40. Okay, if length of unique result equals 1. Yeah, pretty good. Cool. All right, it's done. And what I would do is this. Looks like a nice smooth kind of shape. I wonder, what would it look like if it's going to look weird because it can't, because it kind of, how can it be 0? It absolutely cannot be. Oh, 0 would mean it took one roll. It would be like, and then log would be there for v1. What I'm going to do instead is say simulations log equals x, a qplot trick. Yeah, it's like kind of log normal, like, but remember that there's not really such a thing as log normal here because these are all integer valued. This could be a weird bin thing. There's not, I wouldn't overly focus on that, but that's not the main thing. What I want to know is simulations. On average, about 9 2/3 is how many rolls it takes. What's the most common roll? There's a couple ways I could do this, but I could do it with a sort and a table. The most common roll is 6. I could also have done Pibble. I could also have done this. Count simulations, sort equals true. And then say, okay, the most common roll is 6, followed by 5 and 7. Yeah. All right, so there we have a solution. It looks like on average, it takes 9.666 rolls to get the same number on all sides. All right, that's the solution to the first part of the problem. Second part of the problem is extra credit. Instead of a standard 6-sided die, we have an n-sided die. And notice that I actually kind of looked forward to this. I said, oh, let's use num sides equals 6 with a default value of 6. Let's try a couple values and try, I don't know, 10,000 each. If you've seen my previous simulations, you've seen that I like to use the crossing function and say trial equals 1 to 1,000 and num sides equals, let's see, oh yeah, I said, well, we're never going to do less than 2 because one-sided, it's always instant. Two-sided is actually not that exciting, I think. Two-sided will be, if you think about it, it's like, it could happen on the first one, but if it doesn't, then you know you have two-sided one. It's a geometric process where at each, with a 50% chance for each. So on average, it's going to be 2. So as my prediction is on average, it'll take 2 rolls on when there's two sides. But I'm going to try this 2 to 10. See, 10 is going to be it's going to kind of be slow. I'm going to start with 2 to 8. And then what I'll do is I'll say mutate simulation equals map dbl of num sides. Apply to each num sides the simulate roll function. And then it'll apply this to every one of those simulations. So simulation is crossed. And now I've created all my simulations. I could create a histogram of all of them. Why not? In fact, I'm going to do 2 to 9, so it's a little bit, that'll be 8. Will that look good? That won't look so good. I'm going to do it as like this. 2 to 10. What am I doing here? What I'm doing is I'm saying simulation. I want to see the distributions for each. What I'll do is a histogram, facet wrap by num sides. See, it kind of shifts out. Nope. Something's up here. Yep. Init num sides. See, that was the step I was missing. Did you catch that? I was hard coding the 6 right there. Wonder if this will be fat. Probably be slower because once you get to 10 sides, notice that it'll actually get like. There it is. Yeah. So this 2 is actually going to be an exponential distribution. As I mentioned before, it's kind of a special case where if you fail, you always get right back to the beginning. And I said exponential distribution. I meant a geometric distribution. And as it happens, I believe it's going to be 2. So let's actually group this by num sides and summarize average roll equals mean of simulation. See, it's pretty close to 2. 2, 4, see, I'm going to increase the number of trials to 3,000 each. Might need to go up to 10,000. It's going to slow it down just a little. And but then I can pipe this right into to a graph where I'll say num sides. A two-sided die is it's like a coin. and a three-sided die isn't exactly meaningful, but yeah. So now we have a num sides average roll geom line. Looks pretty linear. I'm going to expand limits y equals 0. So notice it's going up linearly. If I actually take a look at this, it looks like it goes like little under 2, little under 4, under 5, and it like just keeps going. It's going like up kind of linearly. I'm going to increase this to 10,000, make that line a little bit straighter. But yeah, it looks like each side you add is going to increase the average roll by a little bit. That's something we just learned. Love this crossing. A very flexible approach to doing a numeric simulation, statistical simulation. And once that's done, take a minute. I'm just going to say scales equals free y and see how that looks. I think it might look like a slightly better graph. I'm splitting some things up while we're at it. Okay. Yeah, it looks very linear. In fact, summarized. I'm going to save this. Summarized. And why am I saving it? Because I actually want to know what is the relationship. And say it's going to be average roll by num sides, and it looks like it's negative 1.94 plus 1.94, like 1.95, probably like 1.945 or something like that, and then you're adding 1.945 for each side that you're adding. And yeah, this is the graph. You throw in a geom point if you like. It doesn't make a difference. This is that like relationship. Slope a little under 2. Okay, and what do the shapes look like? Well, they look like this, kind of inching outward. Yeah, look at them kind of inching outward. So as I noted, it's going to take at least a few. Once the number gets higher, it will take a couple rolls. It'll almost never happen immediately. Yeah, bin width equals 1. It's kind of like bin width 1 on these graphs. Yeah, I like that shape a little more. Look at how those shift. Isn't that funky? All right, and that looks pretty good. I'm gonna add one last thing. I'm going to find what's the variance of the rolls in summarized. Why do I want to know that? I want to know if they're over-dispersed. These are always counts. If they were Poisson, they would be variance equal to the mean. I didn't think they were, and they're not. In fact, the variance over the at the mean, which is not, it's actually coefficient of variation, is the standard deviation over the mean. But what is the standard deviation? Let's see this. Standard deviation roll equals. I like to just get. So what I'm doing here is if I wanted to do a mathematical approach, I would want to get some hints. I'm going to do a simulation. And I'll say COV, coefficient of variation, is SD roll over average roll. Oops. Standard deviation divided by the average is a coefficient of variation. Coefficient of variation is going down. Yeah, looks like it's going down a little bit. Okay, I don't have any clear hints here, but noting that the variance is a good deal greater than the mean means that it's... yeah, it doesn't look like Poisson. The fact that the mean down here is 17.5, and yet it can be this high. Yeah, I don't know what... I don't know what shape this is. I don't know if it is a classic distribution. I haven't taken a mathematical approach to this yet. Maybe I will afterwards, but I just wanted to show how I would approach this from a simulation. In particular, I wanted to show the accumulate function. which is really great when you say you do a repeating process where every step, the result of that step gets fed into the next step. That's accumulate. Okay, that was my screencast. I'll submit my solution to the Riddler. I hope you had fun. I certainly did. I'll see you next time.